Swayam Prabha. Digital India. Educated India.
The parsing that we are doing is called deep parsing. So we are pretty high up in the NLP stack when we are doing deep parsing because we are covering the underlying tree structure. So the linear sequence of words conceals below it a tree structure. So that is what is getting uncovered in parsing. Now, parsing is a fundamental problem, should be done for all languages for downstream NLP applications, but the reality is that only English has a good parsing solution. Other languages don't. Actually, they have shallow parsers, they have some semblance of parser, but not at all near English. And we'll see the reason why. Now, parsing feeds on input from chunking, part-of-speech tagging, and morphology, particularly part-of-speech tagging. And the reason why we did part-of-speech tagging right at the start of the course is that this is really the feeder for many downstream NLP applications. Even sentiment analysis needs to know which are the adjectives in the sentence, because adjectives carry sentiment, good movie, bad performance, and so on. So adjectives need to be detected. So part-of-speech tagging plays a role there also. Now, while parsing the sentence, we essentially group the words. Grouping is done in shallow parsing also, but here groups are combined to produce bigger groups. Okay, so that's why we say that shallow parsing is non-recursive. Deep parsing is recursive. And here is an example why. So we have the verb phrase, the detective listened with a wooden face. So verb phrase itself contains a preposition phrase. Preposition phrase contains a noun phrase. So this kind of recursivity happens. That's why this is deep parsing. You have tree, subtree, sub-subtree, and so on. This is called constituency parsing. In dependency parsing, we capture the dependencies. Dependency between head and modifier. So a crucial terminology in dependency parsing is head and modifier. The blue sky, sky is the head. The modifiers are the and blue. Okay, so head modifier relationship is identified. Now, to motivate the discussion on parsing, we saw that a downstream large NLP application like sentiment analysis has built into it the requirement of parsing. We want the sentiment on a particular aspect of the entity E. The opinion is held by H at a time T. So the sentiment pertains to a time is attributable to an opinion holder on an aspect of an entity. So you see there are these noun relationships which need to be identified by dependency parsing. So we saw this example. I love the songs in the movie, though only the cast was liked by my brother. And these kind of sentences can be very long, okay, with many entities coming together, loving or hating other entities. So these triples are crucial for information extraction. So opinion holder, sentiment, aspect, triple. I love song, brother like cast. Present tense for I, past tense for brother. Okay, so this kind of grouping is important. So we see that in the text, though the sequence is linear, we need to identify the groups. Now, an interesting question is, deep neural networks have shown a lot of success in natural language processing. And one of the deep neural network models by LSTM goes left to right over the sentence and right to left. How does it capture recursivity? Because recursion is fundamental to language. Sentences are created by recursive process from sub-sentences. So this kind of embedding of sentence within another sentence, how is it to be captured in deep neural networks? Are neural networks built for capturing recursion? Okay, so here I would like to mention that in 60s, and a very important theoretical advancement happened. So this is not on the slide. I'm just keeping this slide and sort of digressing to give you a theoretical underpinning. So Turing machine was shown to be equivalent to lambda calculus and also a network of neurons. A network of neurons with adequate number and adequate non-linearity in each neuron. So this was a proof in 1960s. So since lambda calculus, Turing machine can capture recursion, neural networks also can capture recursion. So the theoretical underpinning is there. But implementation wise, how do you capture recursion? That is something we have to look at when we do deep neural network for NLP. So two kinds of parsing, constituency and dependency. So dependency approach is suitable for free word order languages like Indian languages. Now, the challenge that we understood for parsing is structural ambiguity. A sentence can have multiple parses. So I saw a boy with a telescope, has two parses. In one parse, the boy holds the telescope, and in the other parts, I hold the telescope. And that is indicated by the depth of the phrase, preposition phrase with a telescope. Here with a phrase, the preposition phrase is at the same level as the verb. So saw gets attached to with a telescope. In the other parts, with a telescope is deeper and it is at the same level as boy. So it gets attached to boy. So this being at the same level and getting attached to is founded on a strong linguistic theory called binding theory. Okay, this is due to Chomsky. It's called binding theory. Okay, so Jyotsna, please mention this point, binding theory. Okay, this will be applicable to constituency parse tree. So by looking at the parse tree, I can tell who holds the telescope, me or the boy. Okay, so that's because of the binding theory. Now, a dependency parse tree also produces two different parse trees. Boy with telescope, here boy holds the telescope, and saw with telescope, here telescope is attached to C, that means I hold the telescope as instrument. Then we understood that there is a verb-centric view of the sentence. The verb is at the center, nouns link with the verb through different case relations. So we can look upon the sentence as a stage where there are actors. These are nouns and the verb is the action. So an illustrative example was the main verb read linking to agent, object, instrument, place and time. Okay, the five fundamental relations: agent, object, instrument, place and time. Ram reads a book with his classes in the evening in the study. So here we need to resolve ambiguity because in the is common coming before both evening and study, but we have to give the correct semantic role. So semantic role leveling comes little higher up, even above parsing, because it depends on parsing. So now today we would like to spend some time on grammar and parsing algorithm. So those of you who have done compiler course as well as programming language course would be familiar with at least the rule-based parsing. So let me give an overview of the algorithms seen there. So we have a very simplified grammar. Sentence goes to noun phrase, verb phrase. Noun phrase goes to determiner and noun or simply a noun. Verb phrase goes to verb, adverb or simply a verb. So a rule, a left-hand side expanding in two different ways is a source of ambiguity. So noun phrase can be either determinant noun or a simply noun. Verb phrase can be verb-adverb combination or verb. Okay, so this is the grammar, and this grammar obviously doesn't capture whole lot of language constructs. For example, it doesn't capture question, does not capture command, go there, because the sentence is not starting with a verb. But you can add those production rules also and increase the scope of the language. So now, again, those of you who have done compiler course or programming language, you know that there is always this shift reduce conflict or shift reduce ambiguity. By the way, compiler came from uh, our desire to interact with the computer at a higher level. So computer understands bits and bytes. We understand patterns and strings and symbols. So the translation from symbols and strings and patterns to bits and bytes is the job of a translator or a compiler. And shift reduce conflict is whether to reduce a group of terminals or non-terminals into a left-hand side non-terminal. This is reduce. Or should we look at more input from the input that is given to us? Should we look at more input, or should we reduce to a non-terminal? That is the shift reduce conflict. Now, I'll take this example sentence, people laugh, and mark these numbers, 1, 2, and 3. So 1 is before the first word, 2 is between first and second word, 3 is after the third word, and so on. And at the end, we have n, which is the length of the sentence. And these positions are very important for controlling the parsing algorithm. So these positions are quite sacrosanct. We take note of them. In the lexicon, we have noun and verb for people, noun and verb for laugh. So people can be, most frequently people is noun, but people can be verb also. The city was peopled with soldiers, for example. So this means city was populated with soldiers. So this is a lexicon, and if we don't do part of speech tagging, then we have ambiguity with respect to the words. Is this noun or a verb? Similarly for love, noun or verb. So assume for the time the part of speech tagging has not been done. We only have dictionary categories and the input sentence in front of us. The top-down parsing, which is also called recursive descent parsing, you would be familiar with these terms from your compiler programming language course, goes as follows. So S and 1 indicates the input pointer, okay, the head that moves over the input text. So S is the starting node. S is expanded to NP and VP as per the grammar rule. That's why it is called top down. I take the left hand non-terminal and expand it by the right hand side of the rule. So we have NP, VP, and the head remains at 1. The input scanner remains at 1 because we have not consumed any input yet. Then we have DT and VP. So NP is expanded as DTN. It could have been expanded as N also because NP goes to DTN as well as N. So it could have been expanded as N. So that's why we keep this as backup state. And VP is not yet expanded. And this is 1 still because the input pointer has moved. Now I consume, now I see the sentence as people laugh. I am expecting DT because this is on the stack. Okay, so DT is expected, but I don't find DT. So I have to do backtrack and bring to the stack the backup state. This is NVP1. So NVP1. Now N demands a noun. I consume people. People is consumed, so VP gets exposed. Meanwhile, the input pointer moves to 2 because people laugh, people has been consumed. Now VP is expanded as VADV, verb and adverb. No input consumed, so 2 remains. But VP could have been also expanded as V, the verb. So backup state is V and 2. I consume laugh, which is the verb, and adverb gets exposed. The input pointer goes to 3, end of the sentence. So now no more input, but adverb is expected, the stack is not empty. The condition for termination is stack empty and input totally consumed. So stack is not empty. Therefore, the processing is not complete. So that this is not the right parse. We are not leading to the right parse. So I bring V2 as the backup state doing backtracking. So now V comes back and input pointer comes back to 2 from 3. So the input that was consumed is pushed back to the input. So now I have an expectation for V. This is met by laugh because laugh can be a verb. Now the stack is empty and the end of input has been seen. So stack empty, input over, the algorithm stops. So the parsing succeeds, saying that the sentence is a valid sentence. And now if we trace back the pointers through the stack, then we will be able to get the parse tree people laugh, okay, where NP is people, VP is laugh. So that's how the parsing gets over. Okay, so this is the top-down parsing, very elegant and very easy to code also, because every non-terminal becomes a function and it calls other non-terminals as function from within the body. This is a recursive descent parser. Now the problem with recursive descent parsing or top-down parsing is well known, namely that a lot of useless productions come onto stack and get applied. Even when the input has no such non-terminal, we still apply, okay, and then make mistake, do backtracking, pick up state from the backup. This is one problem, leads to inefficiency. The other problem is it cannot handle left recursion. So if NP gets expanded as NP, this will go on getting expanded infinitely, and the parser will never stop. It will go on generating the same non-terminal. So inefficiency of rule application and left recursion. So this is the problem with top-down parsing. So I hope you understood top-down parsing. Very easy to appreciate how it is working. Now the question is it a machine learning algorithm? Is it a deep learning algorithm? Or is it straight away knowledge-based, rule-based framework? Well, it is straight away knowledge-based, rule-based framework. So, so this is how the top-down parsing works. And the discussion is the kind of searching is goal-driven, gives importance to textual precedence, the rule that comes first. So NP goes to DT, N comes first, and NP goes to N comes second. So the textual precedence is given importance. You first apply the rule that comes first. And no regard is given to data. I know that there is no determiner in the sentence, still I apply DT and expect a DT in the sentence, which is wasteful effort. So, and this is top down, you go from sentence symbol to the whole sentence. Bottom up parsing is opposite, and we have some convention. We have a non-terminal with a suffix, lower suffix, indicating two positions. Okay, N 1, 2 means there is a noun between position number 1 and 2. So S1 question means goes to NP12. NP12 means between 1 and 2, there is a noun phrase. And VP2 question, I think we are probably not able to see. This is VP2 question. That means there is a verb phrase starting at position number 2. I don't know where it ends. So the whole thing is controlled by these positions and this dot symbol, which in programming languages or compilers is called a handle. Okay. parsing came into computer science from linguistics. Okay, it is not the other way. Parsing came from linguistics into computer science. This is an important contribution of linguistics to computer science. Okay, so handle is a term introduced by compiler technology people. This dot is called dot by linguists. So dot, wherever dot sits, it says that I have completed some work that is coming to the left of dot, and I have work to do that is coming to the right of dot, the handle. Okay, so the dot sitting here says that a noun phrase has been resolved. Now a verb phrase needs to be resolved. Okay, so this is the algorithmic construct which is used. So let's illustrate what goes on in bottom-up parsing. People laugh. We have the word people and we have the word laugh. People is preceded by 1, beginning of the sentence. Between people and laugh is position number 2, and after laugh is 3. So this bottom-up parsing, I go from word and reduce. Okay, reduce. Reduce means bring in non-terminals or categories. So n goes to people. So this is n1, 2. But people can be verb also. The dictionary tells me people can be verb also. So I can have v1, 2 here. Now noun phrase goes to n. Here you see, since I have found n, I can indicate this in the rule np goes to n. So between 1 to I have found n, that work is over. The handle moves from left of n to right of n. And I have found a noun phrase between 1 and 2 because there is nothing after the handle. So the work of finding a noun phrase is also done. So people forms the noun phrase. People could have been a verb phrase also because V12 has been found and there is a production rule in my context-free grammar. VP goes to V. So V12 I have found a verb between position 1 and 2, and by applying the rule VP goes to V, I have found a verb phrase also between 1 and 2, and the dot goes over V. What happens to the ultimate rule S goes to NPVP? Well, I have found NP, so handle goes after NP. Now I have to finish the work of VP, finding a verb phrase. So NP is between position number 1 and 2. VP is from 2 to the end of the sentence. I don't know that index. If I know the length of the sentence a priori, then I can put that number here. So now, since the work of VP needs to be done, I go to laugh, and laugh again produces N23. Laugh can be I had a good laugh, which is a noun, and I have V23 between 2 and 3. There is a verb V. So I finish the work of finding NP. Okay, so this is what is going on is the LR parsing, left right parsing. So N2, 3 between 2 and 3 I have found a noun. So NP's work is also over, and between 2 3 I found a verb. So VP's work is also over. So now the dot can move over VP also, and dot has gone to the right of S goes to NP-VP rule, the final rule that discovers the phrases of a sentence. So here I can stop the parsing and say that the sentence is composed of NP and VP. NP is a noun, VP is a V, that noun is people and verb is laugh, and my parsing is complete. Okay, so this you can see is data-driven parsing. Okay, it starts from the data, the input sentence, and goes up to S. In top-down parsing, we start from S and consume the input until it is over, and the stack is also empty. So this parsing goes on reducing the words and the phrases to non-terminals and finally arrives at S. So this is the bottom-up parsing, and it is LR parsing in a compiler or programming language. Now, did I do any useless work here? I did, because for people I got N and V. V was not necessary. For laugh I got N and V. N was not necessary here. But fortunately, the handle or the dot symbol took care of that. So dot said I want a verb phrase, and verb phrase says I want a verb. So the N symbol was not at all used. So even though it uh, came to the computational process, this is called a chart. Even though it came to the chart, it was not used, but still it is useless. So the merits of both algorithms, top down and bottom up, were combined to get what is called top down bottom up parsing. Okay, top down bottom up chart parsing. So it combines the advantages of top down and bottom up parsing. Again, it does not work in case of left recursion, because you first have to apply top down parsing and then go to bottom up parsing. So top down, bottom up, this goes on alternating. But it's a very, very famous algorithm, most probably the most famous algorithm before the CYK parsing, which I'm going to take up after this. So S goes to NP VP, NP goes to DTN or N, VP goes to V ADB and V. So again, repeating that NP goes to DTN and NP goes to N are two different rules. Okay, VP goes to VADB and VP goes to V are two different rules. I could have written them one after the other, but this is a more accepted convention. So now again I have this sentence: people laugh. 1, 2, and 3. I'm reminding you again and again that this position number 1, position between words, and position at the end are very sacrosanct for the parsing algorithm. So I start with S goes to NP-VP, the dot is before NP. Now I do a transitive closure. This is called transitive closure, and it is nothing but the top-down application of rules. Now, dot is telling me I need to find out an noun phrase. Finding out noun phrase is amounting to finding out a DT and N, or simply an N. So to complete the work of NP, you have to find DT first. So that's why dot is before DT, and dot is also before N. Okay, so what have I done is I have expanded NP into DTN and N. This is nothing but top-down parsing. Rule application has happened. And this is called transitive closure, where everything that the dot demands is brought onto the chart, onto the computational process in anticipation. Okay, so this is the top-down part. Now the algorithm switches to bottom-up processing, looks at people and brings in N. Why N, not V? Because you see, the previous chart told me that I need an N, and it did not tell me anywhere in the chart that I need a V. So why should I bring V? I'll not even look at V from the dictionary. I'll bring N. So since N has been found, the dot moves over N. Therefore, the dot moves over NP also, and it sits in front of VP. While this happens, since VP has been brought into focus, the rules for VP are expanded. So VADB and V are brought onto the chart. This is again top down. So I did bottom up by taking NP goes to N and S goes to NP, dot moving over NP. This is the bottom up part. The top down part is VP expanded to VADB and VP goes to V. So this is a combination of top down and bottom up. Now what I am expecting from the chart is to look for a V.